开始连接话筒，开始连接话筒，已解锁，请取出话筒。
Good morning to everyone. So I have received your quiz 2. For some of you that has problem, maybe I'll call you up during the rest. And there's 2 more weeks for midterm, right? So it's on week 9 Friday. What time is it? What time is it? It's on Moodle. What time is it? 7 to 9 p.m. Okay. What's the venue? What's the venue? Have we fixed the venue yet? I think we haven't fixed it. We will let you know soon. Okay. So midterm will be everything up to differentiation. So meaning up to last week. We will make announcement again. Okay. But from today's integration, it will not be in the midterm. So, but it will be in final, of course. And after midterm, we will announce the project. Okay, so maybe I can let you know a little bit beforehand, but we will release more detail after midterm. Yeah, so you could start preparing like we'll have a group assignment. So basically you can do it in 3-person, 2-person, or 1-person. Yeah. So basically it's about solving one application problem, something like that. Yeah, application problem. So if you look at the your textbook, right? Do you see some question like a project question like that? You notice? No? You should read more. It's in your textbook. So in your textbook, there's like a tutorial question, right? Question exercise after section. And in the text, there's like a project problem, something like that. So those are possible title you can take. Yeah, try and have a read first, and then we will announce the format soon after the midterm. Okay, any question or any administrative question? Any question on lecture notes? So some of you found problems on lecture note, for example, typos or miscalculation, right? So just feel free and let me know if I make some mistake, I will change it. Okay, if no question, then we will start the new topic today. Okay, so this is a little bit different from differentiation, which is integration. Okay, so we start with integrals here. So what's the idea behind integration here? So let's look at one question here. So do you know how to find an area of a circle? Although maybe since high school or primary school, you know that it's pi r squared. So how historically people found the relation between the area with r squared? And why the constant is pi, not 2, not half, not 3, not something else? Okay, pi, if you know that it's actually is a irrational number actually. Okay, so you cannot express as a fraction. Okay, so it's irrational, not a rational number. So how do we find this? Well, um, we could put some polygon inside this circle, okay, to approximate it. For example, you could put a square inside your circle, okay? Square, you know how to find the area, right? So the two sides is the same, you just take the product is the area. But you can see that there's some missing area from the circle. Okay, so what people do was I increase the side of this polygon. So meaning I not only put a square inside the circle, but I will put a pentagon. So if you notice that once we add one more edges or one more vertexes, you can see that the area that we cover the circle become small. Okay, so there are less area that we didn't cover. So you can do this process again. So you add more edges, add more vertex to this polygon. Okay, so this will approximate the area of the circle factor. Okay, so this is a Greek way. Actually, Chinese also do this. Okay, Chinese also do this. Chinese was putting the polygon upside from outside. Okay, one of them putting inside, one of them putting outside. Okay, so from outside you can see that it over cover, right? Okay, you see that it's over cover, but once you increase the edges and the vertexes, then the area that you cover extra becomes less. Okay, so it approximates the circle better when you add more and more. Consider larger n-gon. Okay, this is what we call n-gon, 4-gon, 5-gon, or 7-gon, referring to the number of vertexes. Okay, does it make sense? Okay, so how does this link to integral? Later we shall see this. Okay, so basically, what we do is we compute the area of the circle by taking a limit process. So this n is getting larger. So supposingly we know how to compute the area of the polygon. Supposingly you have a formula. Okay, so please remember this idea, area in terms of a limit. And later we will use this idea again and again in this integration topics here. Okay, area using a limit. So we start with some gone rectangle or square that we know how to compute and then approximate something that's not a proper n-gon. Okay, so before that, we'll start learning some notation here. This is called the sigma notation. Okay, so this is a big sum. Okay, so basically, what is it? So what you need is you need to have some term here. Okay, call it AI, and then this I here get indexed. Index mean label. Okay, in the layman term is labeling. So this is label from where to where. So bottom is your starting point. Okay, then the top is your ending point. So let me write down. So here is the so I is the indexing label. Okay, and then the bottom here is the starting point, and then the above is the ending point. Okay. So this I here, where to start, where to end. This I actually should live in natural number. Okay, so if you still remember what natural number is, basically we could start from 0 in this case, 0, 1, 2, 3, and so on. Okay, start with some natural number and then end with a larger natural number here. So meaning you need to sum every term between this and. Okay, So for example, maybe I can write down an example here. So let's sum from let's sum from I goes to, let's say, 2 to 5 of AI. Then we start with A2 plus A3 plus A4 plus A. Okay. So this is a convenient way to write out a finite sum. Okay, does it make sense? Okay. Okay. Let's do some exercise then. Uh, well, let me try one, and then we'll let you try the rest. Okay, let's try the first one. So we are summing I squared again, but we label I from 1 to 4. So what does this mean here? So you start with 1 squared plus 2 squared plus 3 squared plus. Then we stop at 4 squared. And then we start with 1 squared. Okay. So if we try to compute this sum, what do we get here actually? So this, there's only 4 terms here. It's quite easy to compute. So we get 1 plus 4 plus 9 plus 16. And then this is 30. Okay. Make sense? Okay. So try to compute the rest. Okay. If you can compute the sum, then you compute it. If not, later we'll discuss. But try and write down the sum here, all the finite sum. I give you maybe 2 to 3 minutes to write it down. And if you can compute the sum, you compute it. If not, we can discuss afterward. Okay, try write down the term by term sum. You can discuss with your friend, check with your friend. Okay, so let's try B. Okay, so where do you start with B? What number do you start with? Purity. What's the number you start with? Three. Three. Someone help you? Okay, three. And then what's the next number? Four. And then five. And then six. And then where do you stop? And okay, some number and don't know what is it. Well, I mean, so how do we compute this? So this sum for sure is a finite sum, okay, but you can imagine that it gets really large. It depends on this n here. Because if n is 4, it's just 7, right? If n is 4, it is 7. But if n is 5, then you will get 12, like that. Okay, so How do you give a formula here? Well, actually, you can notice that this is a sum that can be obtained by subtraction of another sum. Maybe I write this in another. So maybe we can sum up from 1 to n of I minus sum from I to I from 1 to 2. Okay. Does this make sense? So what I do was I add an extra 1 plus 2 here and then I take it away. Okay. But then why do I write like this? Have you seen this formula before? Summing the sum of natural number from 1 to n. Have you seen this formula before? Yes? Okay, do you know what is it? You know what is it? What is it? Ah, Pinton, you don't know? 1 plus n multiplied by n. What did you say just now? Over. Oh, n plus 1 times n over 2. Let's see, is it correct? Yeah, sure, yes. Okay, later we'll see this formula again. Just I try to motivate you what is going to happen. So if you know this, then you can take away 1 plus 2, right? 1 plus 2 is easy. It's 3. Okay. So minus 3. So then you can simplify this to this. So later we will see this formula. This derivation is quite fun if you want to look at, but we won't do it here. Actually, this formula is derived from Gauss. If you know who is Gauss, Gauss is a mathematics prince. He's a very good in mathematics. So this is basically like I think his primary school or his secondary school, his teacher asked him to like sum from 1 to 100, sum 1 to 100. Yeah, and then he discovered this formula. Okay, next, C. How about C here? Okay, so in this case, you start with 0. Okay, so you put 2 to the 0, and then you end with 2 to the 5. So you need to sum all the terms in between. Okay, fine. So, well, you can do some calculation here. What I did here, instead of I expanding everything, what I do was I do some factorization, I guess. Yeah. So to quicken my calculation here. So I factorize one, factorize second one, then I factorize another one. Yeah, I think I get 63. If you expand everything term by term, you also get 60. Okay, how about the D? Okay, D. Okay, D start with K equals to 1. So what did you notice here? We are not just using I, right? Okay, we are not just using I. We can use different alphabet, okay, to label. Okay, so this labeling could change. So D, we start with 1 over K starting from 1. So we got 1 over 1 here. And also stop at 1 over N. Okay, so there's a bunch of things in between. So N here is doesn't fix it. So anyone know what's the sum here? Can you sum all these together? Well, maybe one thing you can think about is that I make the denominator the same, right? And then I add them together. But you can imagine that you get like pretty complicated. Well, so if you look up online, right, I think this formula is kind of hard. Okay. Actually, this sum is what we call divergent. Okay, what we call divergent. In calculus 2, you will see this. So in calculus 2, you will see this n become infinity, and then you will ask whether this sum exists or not. Does it compute to a finite sum? Okay, so in this case here, this sum is like going to no way. Okay, going infinity, keep increasing, very big. Okay, maybe you can try and look up this one yourself. See how hard it can get. That's not important here for now. Okay, next, sum of this fraction here. Okay, so there are two place appearing I here, so you need to make sure you substitute both places. Okay, so you sum up to 3. So there's a 2 in between. Okay, there's no 2.5 here. I don't put those things in because we only consider natural number. Yeah, yeah. What's the answer for this? If I'm not wrong, it's 1 over 7 plus 2 over 12, which is 13 over 42. Sorry, yeah. Okay, good. Yeah, same. Okay. Okay, how about the last one? There's no I here, so how? Sorry? Yes, just 2. So meaning is a constant here. So how many times? What do you think? 4 times, right? Because you need 1 time for 1, second time for 2, third time for 3, and then fourth time for. Okay. So actually you got. Okay, so on other notes, right, you can write this as 4 times 2. Okay, 4 meaning uh, how many times you add them. Make sense? Okay. Yeah. So this 4 doesn't just fix with this ending point, right? For example, I can add from 0 to 4. So how many times you add actually? Okay, actually in this case here, you add 5 times. Okay, because you start with 0. One more term extra. Okay, so don't just look at this 4 and then you just multiply 2. Make sure you know where to start here. Okay, so far makes sense? So far? Okay, good. Question? Any question? Okay, let's continue. So there's some property of sigma here. Okay, so if you sum of scalar multiple of AI, you can pull the scalar up. Or if you sum of a sum, okay, you can just compute the individual sum and then sum them together. What's this kind of property called again? Do you remember? You can pull out the scalar, you can split out the sum. What's this property called? We met this in limit chapter, we met this in different derivative chapter. You should meet it in your linear algebra as well. Okay, so this means that sigma is linear. Okay, anything that you can pull scalar out, okay, before operation, or you can split the sum, this is called linear. Okay or not? So TCX equals to CTX, and then EX plus Y equals to EX plus EY. Okay, so T here could be sum, could be limit, could be derivative. They are linear. T is linear if these two happen. Okay, please remember this property here. Uh, however, what you have learned now is linear, so it's a pretty nice property. Okay, so 5.2. So what can you do? What can you do? What are you going to do with this? So given a sum of AI from 1 to 100 is 60, and 1 to 100 is of BI is 11. So we don't really care what is AI, BI here. Okay, just what we care is what's the total sum here or the finite sum here. But you are asked to find a sum from 1 I goes to 1 to 100 of this linear combination. Okay, is it okay? I use a linear combination here. You know what linear combination is? Hi, linear algebra. Linear combination of vectors. Scalar multiple, sum of scalar multiples of things. Okay. So this is a linear combination of AI, BI, and um, number 1. Okay, 1. 4 times 1. Okay, so since sigma is linear, and then we could just split up the sum. Okay, so let's see how do we split it up. So basically, we just split up by the summand first. Okay, and then we can pull the scalar out. Okay, we can pull the scalar out. So 4, do we have anything to pull out here? We could do like 4 times 1, for example. We can make the constant even easier. Or you can straight away compute already, right, for this term here. Just now we said that this is like 100 times 4, right? 100 times of 4. Okay, so next, you apply assumption. So sum of AI from 1 to 160, and then minus 3 times 11 plus 4 times 100 times 1. Again, 100. Okay, so altogether you get 400. Any question? Pretty, you look a bit confused. You should ask question. Otherwise, you go back confused again. Question? Sorry? Don't have question? You don't understand? Yeah, so from which line you don't understand? So we need to pin down. It's okay to not understand, but we need to pin down which part is your confusion. You should start at the confusion point. Maybe tell me what's the first confusion point. Sorry? Previous part, okay, we could go back to previous part. So where is it? Which line? A, okay, A. So what's wrong with A? How do we get 2, 3, 4, right? So there's something you need to understand here is where should we get this I from? Where are we getting this I? Okay, where my laser? Where are we getting this I? Okay, so this I here is living in this set here. 0, 1, 2, 3, 4, and so on. Okay, this is what we call a natural number is. Okay, so if we pick a starting point 1, okay, and the endpoint 4, we should add up all the points in between. Make sense? So there is a sequence, there is an order here, which is the natural number order. You need to keep in your mind when you read this or this summation here. So meaning there's no 2.5 here, no need to add like 2.5 here. Nothing like that. Because this is not our index set. Our index set is natural number. Okay, so similarly, yeah, for upgrade version, right, you can make it into Z, meaning I can sum from like negative 1 like that, right? I can sum from negative 1 to like 100 also can. Okay? We can change this index set, but for this class, we will keep in the natural. Okay, make sense? Okay, good. Better. Yeah. So please ask a question because if you start, you forever start. But if you can tell me what's the question, we can unstuck you. Okay. So happy with this question here for 5.2. Good. Okay. Feel free to stop me. Yeah. Okay. Next, let's try this. Show that this sum of ai plus 1 minus ai is equals to an plus 1 minus a1. Okay, so this n here is get fixed by this n point. It's not changing yet. But what's this sum here, for example? This sum here saying what? Your previous sum, there's a previous term here, ai is negative, and then the next term is positive. Okay, can you imagine what happens here? Maybe we write out a few terms to see what's going on. Okay, let's write down the I equals to 1 term. Okay, So I equals to one term is A2 minus A1. Okay. How about I equals to two term is A3 minus A2. Okay, and then so on. Did you see any pattern here? You see any pattern here? Huh? What's the pattern here? What's the pattern here? Do you see any pattern? Or need more terms to see pattern? Maybe write one more. You see pattern? So what's the pattern? Cancel. Okay, so what cancel with what? So you can see that the A2 and minus A2 cancel. Okay, and then A3 minus A3 cancel. And then A4 minus A4 cancel. Okay, and then keep cancelling. Okay, so the one that doesn't get cancel is the starting one and the last one. Okay, the starting one and the last one. So the last one should be the last one. Okay, all the middle term get cancelled. Okay, sometimes we call this a telescopic sum. Okay, so in the middle term, all cancel. Okay, so you just left with the starting point and the ending point. Okay, does it make sense? Okay, yeah. Actually, to prove this precisely, you need an induction argument, but for now, I think if you can see the pattern, then it's pretty good, yeah, for this level. So the middle term here, the middle, we'll call it alternating terms, actually cancel. Okay, okay, so if you see this kind of a sum, okay, that is alternate between the next term, the subsequent term, then this kind of sum is easy to compute. Okay, for example, the next question here. Okay, the finite sum of I plus 1 square minus I square. So this is a difference, okay, in between uh, subsequent term. I mean, subsequent sequence here that you see here actually is I squared. Okay, I squared here. So the I plus 1 term is I plus 1 squared. Okay, so if you use this formula that we proved just now, use the proven formula. Okay, we will set our AI to be I squared, okay, such that AI plus 1 is equal to I plus 1 squared. So if we want to sum a finite sum from 1 to n of I plus 1 squared minus I squared, is just the an minus 1, sorry, an plus 1 term, so meaning m plus 1, n plus 1. Actually, you need another plus 1 because I become n plus 1 minus ai. So I is equals to 1, so it becomes 1 squared. So altogether, you get, simplified it to get n squared plus 2n plus 3. And follow? Question? Any question? Question? Yeah? Yes. Yes. Which part? Which part? Okay, so to compute that finite sum here, we viewed it as the case that we had before. Okay, so how to build it? So you need to determine what is your AI first. Okay, if you notice that if we set AI to be I squared, the I plus 1 square is exactly the AI plus 1 term. Okay, so you really have a finite sum of AI plus 1 minus AI. So you can use that formula. Okay, if you use that formula, it tells you that it's just the negative of the first term plus the last term, n plus 1. Okay, so you just put your n plus 1 into your AI. Am I wrong? Oh, this is extra plus 1, isn't it? Yeah, this is extra plus 1. Okay. So this is just n plus 1 squared here. Okay. And then take away a1. So a1, you put a 1 here. So 1 square here. Okay, so then this final answer is wrong, right? So this final answer should be, let's compute it. N squared plus 2n plus 1 minus 1 should be n times n plus 2. Okay. Yeah, so the n plus 1 term, so you put your I equals to n plus 1, so here n plus 1. Okay. Is it Aaron? Aaron, yeah. Okay. Better. Oh, got more questions. Okay. 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 Let's continue. So there's some formula here that we not define. But the first one is obvious, right? We just now we see similar sum before. So if you just sum 1 from 1 to n, you just constantly add 1 n times, so you get n. And if you sum, this is a sum of natural number, finite sum of natural number. Again, from 1 to n, you get n times n plus 1 over 2. If you sum I square, it's not too far away. You will get n times n plus 1 times 2n plus 1, 6. And you sum cube, we still have a formula, which is n times n plus 1 over 2, everything squared. Okay, so it's like a number 2 squared. And then lastly, we also got a formula to I to the 4. Okay, maybe you can look up what is the fifth power of sum, etc. 6 power, 7 power, can look up online. Okay, so by knowing this, we're trying to derive formula for different sum here. Okay, so for example, this sum. Okay, do you think it's possible to do this sum based on what we had? Is it possible? Okay, so first thing first, what you should do is you should think of how to simplify it. Okay, did you see anything that you can factorize out? 1 over n, right? Everyone appears with 1 over n. Okay, so maybe you can put out the 1 over n first. Okay, and then we live with this big sum here. Okay, we live with a big sum here. But can you notice that this sum we can write it as a sigma notation? Okay, because you have all the natural number in between 1 and n. Okay, correct or not? You see 1 over n, 2 over n, 3 over n, 4 over n, 5 over n, 6 over n. Okay, up to n over n. So we can simplify this notation here using the sigma notation. So where we label the numerator. Okay, we label the numerator. The bottom is still n. Okay. So, well, this is not close to any formula we have, right? We only have I or I square, I cube, I 4. So there's something extra here. Okay, let's move this up. Okay, can we move this up or not? Maybe we can take square first. Yeah, let's take square first. I square over n square. Okay. So now the claim is I can pull this n square out. Okay, because the sum is linear. Okay, I can pull the scalar out. Note that this n are some fixed number here, or this are fixed number here, because you can think of like what is R100, what is R10, what is R55 like that. Right? These are fixed for some n. The thing that's changing is I. Okay, I change from 1 to n. But now, then we are good already, right? Because we know what's the formula for sum of I squared. Okay, for random n. Okay, this is exactly what is it? I don't remember formula. N times n plus 1 times 2n plus 1 over 6, like that. Okay, so you get n plus 1 times 2n plus 1 over 6n squared. Okay, so meaning what? If you compute this n number by number, it follows this formula here. Okay, so 100, if n equals to 100, you get the, the sum that compute to this n equals to 100 using this formula. Okay. Any questions so far? Should we test this formula? Do you want to test this formula or you are happy with this formula? Should we test this formula? Maybe let's test this formula to get an idea on what actually we are doing here. Maybe let's look at R2. What is R2 here? 1 over 2 times 1 over 2 squared plus 1 over 2 of 2 over 2 squared. So you get 1 over 8 plus over 2, which is 5 over 8. Okay, so if you put the number n equals 2 here, what do you get? So this formula will implies that you get 2 plus 1 is 3, and then 2 times 2 is 4, 4 plus 1 is 5, over uh, over 2 times 4, sorry, 2 squared is 4, 6 times 4 like that, and 3 and 6 simplify, you also get 5 over. Yeah. Okay, so this formula are actually working for random n. Okay, any questions so far? So far, so good. Question? No? Okay. In that case, then we continue a bit more, then we'll take a break. So now this coming to this idea here. So finding the area of a region bounded by the curve. Okay. So this is not the circle we are looking at just now, but similar. Okay, we are looking at some area under this curve here, meaning this part here. But we don't know how to compute it for now. Okay. What we will do is we will start with what we know, some area that we know, which is a rectangle. Okay, we'll use rectangle to approximate it. Okay, so let's look at this four rectangle here. So this four rectangle here have the same width, okay, which is 1/4, I guess. Yeah, 4. Okay, so how about the height here? Okay, so how about the height? So if you can see that actually we are taking the height to be the f of the left end point here. Okay, does it make sense? Left of the left end point of your rectangle. So if we use this so rectangle here. So what's the fourth one? Did you see the fourth rectangle here? Can you recognize what's the fourth one? So there's like 1, 2, 3, right? Where's the fourth one? Where's the fourth one? Based on this, can you guess what's the fourth one? Where's the fourth rectangle? The question said there's four, right? So what's the first? Is it the fourth one? Yeah, it's an empty one. Okay, because if you take the f of 0, the left end point, then you just get 0. So the height is 0. So they count this as the fourth one. Yeah. So that's the empty one, empty rectangle. Okay. So how do we estimate the area here? So basically, copy to us, we take the height. Okay, maybe let's call our y to be fx. It's easy to write down the height. Okay, so the first one, the first rectangle is f0 times 1 over 4 minus 0, and the width times the height. So the height you take from the left end point, and so the left end point here. And then the second one, the left end point is 1 over 4, and then you again compute the width. Then the third one, and then the fourth one. Okay, so something you can see that is these width are uniform. Okay, the width are uniform. Okay, meaning the width of the rectangle. They are uniform actually. Okay, so if you compute this, you get something like 57 over 64. Okay. Okay, so what can you see here? This estimation is not really accurate. Why? Because there are something that you are not covered. There's some area that you're not being covered by your rectangle. So what do you think we can do next? Next, we are still using rectangle. Okay, we're still using this left point method here, left end point methods, but we'll introduce more rectangle to it. Okay, so can you imagine that if I decrease the interval, the width of this rectangle, the next rectangle will fill up the space more. And so let's look at this picture here. Oh, okay. Maybe this picture. Okay. So if I decrease again the width of rectangle, again I build out the rectangle, and then I take the left end point as the height as well. Can you see that? You see the area that we cover is getting more because the area not covered getting less. Okay. So let's prove this fact here, and then we will take a break from here. Okay, let's take this. Uh, let's prove this fact. So supposedly you should expect that this area should be greater than 57 over 64. Okay, we want to prove this. Yeah, let's do it. Okay, so this width here, if you can recognize, actually we are using uniform width as well, which is 1 over 8. Okay, we divide into 8 portions here. Okay, and then what's the estimated area here? So you expect there's like 8 rectangle to compute, right? Okay, so again, the same first 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 rectangle has 0 height because the left endpoint is 0. So 0 square is 0. And then the second height should happen at f of 1 over 8 times 1 over 8. Okay, so since you can see that their width is the same, right? Actually, I can just pull the width up, and I just multiply the sum of their um, sum of their height. Sum of their height here. So the next one is, what should you expect? 2 over 8, 3 over 8, 4 over 8, 5 over 8, 6 over 8, 7 over 8. Is it enough? Is it 8 of them? 1, 2, 3, 4. Oh, we got like 1, 2, 3, 4, 5, 6, 7, 8. Okay. So what did you see here? Actually, there are so many sum here, right? You can apply the sigma notation we have learned just now. Okay, to write this down. So it is sigma of I equals to 0. Okay, up to 7 of f of I over 8. Make sense? Okay. So see if we can use the sigma notation to help us to compute this instead of just evaluate every number. Okay. So um let's apply f of I to the 8. So this is I square over x square, right? Okay, which is equal to what? 1 over 8 times x square of sum of I equals 0 up to 7 of I square. Ah, this is the sum that we have encountered before, right? Okay, finite sum that we've encountered before, but not exactly, because we have an extra term here. Just now you start with 1, here start with 0. But we know that this 0 term is just what? 0 squared. It's just a 0. So it doesn't change the sum. Okay. So we can actually reduce to sum from 1 to 7. Okay, then this is what we know. What's this formula again? What's this formula? The I square one. The I square one is 7 times 7 plus 1 times 2 times 7 plus 1 over 6. So anyone can simplify this quickly? Can simplify this quickly? Maybe use your calculator. Can simplify this? What's this number here? Huh? What did you get? 1 over 3? You sure? How come you get 1 over 3? So this is 8, right? This 8 can cancel with this 8 here. And then the rest you need to compute. What do you get? Huh? What do you get? 7 plus 6. Like this. You sure? The rest? Any other solution? I have a x square here. I got a 7 here. I got a 14 plus 1 here. Right. What do you get? 35 over 124. 38. Okay, good. I got it as well. Okay, so is this number greater than 57 over 64? No? Hey, this is. Or did I make mistake here? Did I make mistake here? Because this is larger. This is not good. Hey, what's this? I think I make mistake here, right? Hey, where I get this 57 over 64 from? Oh, I copy a wrong answer. This one should be 7. Okay, so let's cancel this. This is the answer from the bottom. So this is not. This is 7 over 32. Okay, let's check 7 over 32. Is this greater than 7 over 32? So if you multiply by 4, it's 28 over 100. Okay, it's slightly larger. Okay. Okay, we will save this answer for the next part. We will come back for the rest for the next part. Okay, everyone have question for this first before we close this part? Any question? Oh, here got question or here? Yeah. Purity got question? Can follow? Okay. Okay, so we really have increasing area covered. So you can imagine that what we're gonna do next is like maybe we can take nine of them, divide into nine uniform part, 10, 11, 12, 100. So to get everything right, you really need to do your limit up to infinity. Okay, because at every finite stage, you for sure you will be missing some area. So you need to make your rectangle with a infinitesimal small width. Okay, until you can imagine that your rectangle is like a pin, a lot of pin downstairs here, such that you can fill out this area. Does it make sense? Okay, later we'll make this a bit more precise. Okay, let's take a break until 11:09.
你是在4楼？
对，还是在这里。啊，这是什么时候用？
是在这个月25号，
什么
他
event？
们要去，
那个他原地啊？
不是太原地，是另外一个，我看一下这 My Tech，My Tech 对，
是什么 event 来的？
是讲是 Braden 他 Intake 的那个 company，他们做一个 event，
OK，这个是一面吗？
这个是一面。
现在
不是双面。
OK，
谢谢等等。
如果没有指明还要讲。
Yeah. Does this one actually have an answer we could write? Does this have an answer we could write as of now, or
Yeah, we did right just now. We just did because we know the sum from 1 to n. This is just deleting the first two terms. So just take this one, delete the first two terms.
we just use this to get the
This and then take away 1 and 2. So minus 3.
straight?
Yeah, so this is what we had computed. Okay, minus 3.
Is it because of this
Mhm.
that we put minus 3 on it?
No, because yeah, it is because of this, but not just because this 3. It is because of the first two term is 1 plus 2. 1 plus 2 is 3.
So the sum of this,
Ah.
like, so the sum of the missing numbers.
Yes.
Yeah, how about this
Mm, yeah, this one. This one we should apply this.
This.
Yeah.
This to this.
Apply this to this.
This to this.
Yeah. So how do you view this AI? I mean, how do you view this as an AI term? So you should set your AI to be I squared. So your AI plus 1 is I plus 1 squared.
So it's said.
Mhm.
So it's ASI.
What do you mean? AXI.
So it's said like that's A equal I. That's
AI equals to I squared.
AI equals I squared.
Yeah. So your AI plus 1 is I plus 1.
Okay. Thank you.
See her here. Yeah, learn here. Learn here. Okay. 瑞阳，若是迟慢，意难，玉涛，一则 例文，瑞眼，邓瑞眼，泽汉，嘉来，嘉诚，OK，嘉怡，齐军，疫情，俊逸，相思，意林，冰珍，嘉团，浩云，文琪，汉翔，俊杰，新阳，OK，万达，心愿，玉恒一田冰城，浩然，oh yeah, right. Desmond here or not? Desmond, not here. Oh me, God. Yeah. Chongyi, did you submit your quiz? No, why not? Have you tried? Why not submit? I mean, like even if you cannot finish, you should submit, because if you don't submit, it's zero. If you submit something, it's greater or equal to zero. Fair enough. Yeah. So if you miss any assessment, right, it might have a big impact on your score later, right? It could be because of this assessment you fail, or make sure you grab every chance to earn marks. Okay. Yeah. So please do better next time. Okay. Injie, Gopagani. Where's Gopagani? Not here. Actor here or not? Thank you. Jose. Hisham. Daniel. Outside. Hashim. Is Hashim here or not? Big Yusuf Hashim. Not here. He got a problem with his submission. Anyone is his friend? Anyone know Hashim? You know Hashim? You know Hashim? He got some file submission problem. Can you ask him to contact me through Teams? I already messaged him. He haven't replied me. Please let him know. Okay. Madia, Aaron, got Brandon, back. Brandon. Okay. Alicia, Gunakanti. Okay. Margaret, Hassan Khalid. Is Hassan Khalid still exist or not? No. You know him? What happened to him? Or change course. So he's still in this university? Or which course he go to? No. Okay. Okay, good. That's very good. I think you are better than the academic affair here, because the academic office didn't reply me. Okay. Javed. Gabriel. Jeffrey. Where's Jeffrey? Okay. Purity God. Chen Fan. Yating. Where's Yating? Okay. Wei Ye. Yep. Hong Liang. Good. Okay, let's continue. Okay, let's continue doing this rectangle business here. So let's estimate this rectangle, this graph here from above. Okay, instead from bottom, we take from above. The rectangle we take here, I mean the width we take here is still the same this time, 1/4. But this time we will consider the height as the value on the right hand point. Okay, value on the right hand point here. So you can see that all this rectangle kind of grow up. This is due to our function, okay? So let you try this, okay? I already give you the answer already, right? 57/64. See if you can get this number or not, okay? Let you try this for 2 minutes. See if you can get the area of this time. See if you know how to set it up. Okay. Okay, let's see. Did you get the same rectangle as mine? Okay, so the first rectangle here, using the left right hand point, sorry, right hand point is f of 1/4. Okay, so again, for easy writing, let fx equals to y, which is square. And then we decide that the width is uniform, right? Similarly, we can pull this 1/4 out. And then we add the rest of the endpoint together. Okay, so there are 4 of them. If you like, we can write this in the finite sum notation. So I goes from 1 up to 4 of f of I over 4, okay, which is 1/4 times sum of 1, 4 of I over 4 squared, okay, which is again 1/4 times 4 squared. If you compute it one by one, is fine. Just that I want to show you what we have learned, how to apply what we have learned. Okay, so we need to get our glory formula, which is 4 times 4 plus 1 times 2 times 4 plus 1 over 6. All this 4 will cancel. And we should get 57/64. Okay. Everyone get the same rectangle? No? Everyone got the same rectangle? So this is using the value of the right hand. Okay, got it. Or question? Any different? If you have any different, we set up your rectangle, you should ask now. Otherwise, use. Okay, so what did you observe here? Can you compare this number with 7/32 again? All right, this is way large. And this is way large. This is way large. Okay, but also you can see from the picture, right? There's a lot extra you cover already. There's a lot extra. Okay, pretty lot. Like 57 and 14. And there's a lot that you extra covered extra. Okay, but similarly, if you think about it, if you add more, okay, if you add more rectangle to it, what happens? And then consider the value of the right hand point. Actually, this rectangle will decrease, okay, reduce, reduce in size, okay, in this case here. Okay, for example, this case. Okay. You can see that the area that it cover here becomes less, right? Because if you compare with the previous one, right, what happened in the previous one was like this. Okay, there's like something extra that you cover. Okay, so we make it less. Okay, so you should expect that this calculation will give you a smaller value than 57 over 64. Okay, so let's tell you what this number is. You can try and compute this at home. So this is 51 over 128. Okay, just now what do we get? Let's compare with 57 over 64. Okay, which is 114 over 100. Okay, so we become less. So if all together, right, this is what could happen here. Okay, this is what could happen. So at the top picture here is estimating from the bottom, and then from the second row here is estimating from the top. Okay, so you can see that if you estimate from the bottom, when you increase the number of the rectangle here with the same width, the area here, the estimated area here kind of increase because you get closer to the area under the curve already. And similarly, on the other hand, if you approximate from the above, okay, when you increase the number of rectangle, the estimated area decrease. Okay. But both of them are approaching to the area under the curve. And you can see that these numbers kind of converge, like getting very close to each other, 0.333 something. Okay, and then they'll slowly get to the, you can imagine that they slowly get to the same number. Okay, so this is the idea. Any question? Yes. Huh? 5.6, yeah. Mm-hmm. What happened? Yeah, for 4.6, yeah.
Is the answer actually 57 or 64?
What did you get?
I get like 45.
45, 96? 45 over 96. Let me see. Oh, this is the number. Oh, you can't reduce further. I mean, 45 over 96. If this is true, you can still simplify, right? But your simplification is different. Let me see. Let me check my answer. What the other get? What's the other getting? So let me simplify yours. You get 32. See. So no, I cannot simplify more. Right? Okay, never mind. So let's compute this then. So this is 5 times 8. Oh, seems like you are quite close then. So how do I get my number? Let me check. 52, 56, 57. I initially just compute term by term. Do everyone get this? 15 over 32 for this one. Everyone got this or not? You got this? You got this as well? Okay, then I feel like should be correct because this is also something from the formula, right? Then what's wrong with mine? I compute term by term. Okay. Okay, let's check quickly here. So I compute term by term. Over one, and then what's wrong with my calculator? Oh, I guess something wrong with the line. Oh no, 9 is okay. 9 over 16. Oh, ah, okay. I think here I forgot the 64 here. Then the rest is fine. So, yeah. So this one should close to be fine. Fine. Or this is 35, 30, 30 over 64, 15 over 32. Sorry, yeah. Yeah. Okay, good. Yeah, you're right. 15 over 32. Good. So let's compare 15 over 32 again. So here, 15 over 32. So this is equal to 128 over 60. Okay, still less than that. Okay, good. Yeah. So far, okay. So far, so good. Okay. So the idea here is this rectangle business here, right? Will when you get smaller and smaller, it will fill up the area under the curve. Okay. So let's quickly look at one application topic before we go to the real business later, definite integral. Okay, so the distance is defined to be a velocity over time. But how do we view it inside this graph here? Okay, what does it mean by velocity over time? So let's look at this real life situation here. So an object is traveling along the x-axis in such a way that its velocity v at time t is known in the Venn diagram. How far it travel between time equals 0 and time equals to 24. Okay, so the previous formula, right, it only works when the velocity is constant. Okay, when the velocity is constant, it will work. But in real life, right, your velocity is changing. Okay, and every time it's different. Okay, meaning what? For example, from time 0 to 5 here, we know that the acceleration is the derivative of your velocity. So meaning that actually your acceleration is increasing. Okay, when time equals 0 to 5. But when time goes to 5 to 15, this velocity is constant. So stay the same. There's no acceleration. And then from 15 to 25, it decreases. Okay, so deceleration. Obviously, the velocity becomes less. When you decelerate, your velocity becomes less. Fair enough. When you go through the bump in the LY9, you have to slow down. Did you guys know there's like a lot of bump get set up near the hostel area? Correct? Yeah. So people are complaining about the bump is too high, scratches the bottom of their car. If you can go around the bump and see, right, you can see a lot of scratches now. You can go and take a look. Okay, so then in this case here, what's the distance then? Okay, we only know how to compute when distance is the same. Okay, this average velocity here. Okay, but if your velocity is changing, how to compute here? Okay, how to compute here? So again, it's the same. Okay, it's the same. So like the idea we had just now. So we couldn't compute the exact distance at one point, right? Because there's no time here. Where's the time? So maybe we can put the time longer a bit. Okay, we can put a time longer a bit to estimate the distance. But the point here is we can make this time infinitely small. Okay, infinitely small. But once we make this rectangle infinitesimally small, right? What could happen? Actually, what you get is just a triangle here. Okay. So meaning what? So meaning if you want to compute the velocity that is changing across the time here, you just get the area under the curve. Okay, but the point here is area under the curve here is some geometry, is some polygon. Okay, for example, if you fix your time from 0 to 1, it is actually a triangle. You know how to find the area of a triangle? You know, right? Okay, the height times the width multiplied by half. Okay, and then from 5 to 15, it is a square. Okay, so you should compute what is the area of a square. But the last one, what is this shape here? From 15 to 25 seconds. What do you call this? Trapezium. Okay, trapezium. Okay, do you know the formula of area of trapezium? Half times the sum of these two sides here, and then multiply by the base. Okay, so let's write this down. So by refining the rectangle, so this is actually the distance equals to velocity times enough. Okay, rectangle under the graph enough. Basically, what we are dealing is a triangle, a square, and a trapezium. Okay, more generally, this is actually a rectangle. We call every four-sided. I mean, every four-sided with opposite side the same length as a rectangle. Okay, so what's the total distance here? So the total distance traveled is actually equals to half times 10 times 5, or you want 5 to minus 0 to be precise. And then plus, what's b here? Part b here is 10 times 15 minus 5. And then the last part is half times 10 plus 5 times 25 minus 15. Again, you get a total. Okay. Yeah. Any questions so far? Questions so far? Maybe on a side note, why is this area of a trapezium is half times a plus b times c? Do you know how to derive? Do you know how to derive from whatever you know? Any idea? Do you know how to derive this? Actually, it's very simple. Trapezium, right? If you make the extra line here across, what is it? It is actually a rectangle plus a triangle. So you just compute what's this rectangle here. Okay, so maybe we call this x, and then the top here should be a minus x, right? So triangle is half of a minus x times c plus the rectangle should be so actually this x is b, right? Because it's the same length opposite. So here become b, a minus b. And then the bottom is just bc. Okay. Then it should add up to, if you add these two things together, it should be the bottom one. And see or not? Right. Because bc is just 2 over 2 bc. So minus half bc plus 2 over 2 bc is plus half bc. So that's why it become an addition here. Okay, so this is just a side question. Okay, please be sure to do these exercises in your textbook so that you can learn better this topic. Okay, so let's continue. So we will finally deal with this Riemann sum here. So this is exactly what we have did just now. Okay, so how we start this? So let's read this paragraph together. So consider a function defined on a closed interval a b. Okay, so you should imagine that you have a interval a to b like that. Okay, and then divide this into n equals sub-interval, like what we did just now, like 4 interval, 5 interval, 6 interval, 8 interval. Okay, then we have this labeling here. So this is x0 and x1, blah blah blah, x2, okay, up to xn here. And then the distance here is delta x. Okay, so the delta x here is b minus a over n. Okay, b minus a over n is what? B minus a is the length between a and b, and then you divide by n. It's a uniform width here. Okay. And then next is within this interval here, we just pick some random xi star here. Okay, we pick some random xi star at every interval. But the xi star that we picked just now was either the left endpoint or the right endpoint. Okay, but the general theory is random. No matter it's left or right, don't care. As long as it's in between. Okay, it's sub-interval here. Then we will say that, okay, so you can see that we have put some notation that you have learned before together. So we learn limit, okay, and then we just learn sigma notation here. Then what is this term here exactly? Do you know this? F is the value, right? Delta S is the width, right? Actually, this is the rectangle. Okay, this is the area of the rectangle. Area of so what's this rectangle here? So this rectangle here has a width of delta x. And then the height is f of xi star. Okay, just now we take si star to be either left or right endpoint, but here is random. Okay, don't care left or right, just as long as stay inside the input sum. And then we sum them out. This is what we did just now, right? Sum 4 rectangle out, 8 rectangle out. And then this n to infinity, what does it mean? Sum more and more rectangle. But the way to obtain this rectangle is by making the delta x smaller and smaller. Okay, making this delta x smaller and smaller. So meaning we take the width smaller and smaller, at the same time we take more rectangle. This is exactly what is described here. Okay. Yeah. Okay, we take the width smaller and smaller, but at the same time we take more rectangle. Okay, so this is we have efficiently described this process here using limit, using sigma notation. Does that make sense? Okay, so we use this notation here to describe this process. Okay, we make the width smaller and then we add more rectangle. Okay, so the point here is we ask the question, if this limit exists, okay, like what we do in chapter 1, right? Either the limit exists or not exists. If it exists, we will say that this is the indefinite integral of from a to b. Okay, if this thing here is computable. Okay, we don't care what's formula here, and we don't care what's the formula here. As long as this limit exists, we will name it as the integral sign here, this big S here, from a to b of fx dx. We call this number like this. That's it. Okay. So now you can imagine why we need to teach you the sigma notation first, because if you really want to compute this, you need to compute the finite sum first. And then once you can imagine that we got a formula in n, and then we can compute the limit. This is like the chapter 1, right? So let's give you an example. For example, maybe this sum here, maybe sum to like n of like n plus 1 over 2, n plus 1 over 6, right? Then this return to your chapter 1 question. Can we find this limit or not? If this limit exists, then we call this number. Then we call this symbol here, integrate from a to b. This is the interval that you do your Riemann sum, and then this is your function, and then the extra dx. Okay. Actually, this is also kind of a rectangle here, right? Fx times dx. So here is fx. This is delta x. This is dx. But then we replace this horrible sigma and limit here to this integral, very nice integral sign. Okay, instead of looking this every time, you write integral sign. Make sense? Yeah. Okay, so what's the picture here? Okay, so before that, a and b are called the lower limit and upper limit respectively, and then the thing that you put inside this integral sign dx is called integral. Okay, so this is the picture. Okay, instead of the approximating from the above or from the below, we just estimate at any f of xi star. Okay, you can see that some of the rectangle go beyond the graph, some of them lie below. Okay, but you also can imagine that if I take more rectangle, this extra estimation or underestimation will get less as well. Okay, will decrease as well, but irregularly. It's not like previous case, it's like decreasing, or the other case is increasing, but here it's like irregular, up, down, up, down, up, down, up, down. Should I show you the video next time? Maybe I can show you, I can try and find the Riemann sum video. I try to show you. If not, you can search online. I think this. If I can get it, I will show it next class. Okay, so the same idea is if you get more rectangle, then your area of your rectangle is just area under the curve. Okay, if it is possible. Okay, we still have time. Let's go on. Okay, let's do this. Okay, compute this rectangle, this definite integral here using the definition of integral that we had introduced just now. So let's look at this picture here. So what's this graph here? 2x squared minus 8x. So let's set fx equals to 2x squared minus 8x. Okay, so make sure you know how to graph this. Graphing is a very important skill in this class. Okay, so you get this 2x times x minus 4. So we have managed to find the root here. So one of the root is 0, and then the other root is 4. Okay, but this is quadratic, right? So it's a smiling face, right? Parabola. So smiling face is like this. Okay, but the point we only care about is -1 to 3. So this is the region we care about only. Okay, make sense? Okay, so if we use the rectangle method, right? What can you imagine here? Let's say we use this rectangle method of, let's say, with width of 1 here. Okay, then your rectangle maybe look like something like this. Okay, make sense? Or this one too far already. you need to at least touch your graph. Okay, clear? Does it make sense? Okay. So, but now in this case here, we're going to consider a general n. So, what is delta x here? Delta x here is b minus a over n. So, meaning you take the length of your interval and then divide by n. Okay, divide by n. Because this n we should be growing. Okay, we should be growing here. So, in the previous case here, what's my n? 1, 2, 3, 4. So in this case here, right, my n is 3 over 1, 3 minus 1 over 4. Is that right? So 0 to 1. Oh, then in this case here, I draw too many. So maybe it's just 1. Okay. So in this case here, we get 3 minus 1 over n, which is 4 over n. Okay. And then what is xi here? So what's the next term? So the next term is like -1 plus I times 4 over n. Okay. Because this is our formula. So what's our formula here? So it's a plus I of delta x. Okay. So in this case here, you can also see from this example. So here, what is xi? Labeled it. So we start with x0, right? x0, x1. Okay, x2, what is x2? So 1 here, x1, x2. And so these are x2, x3, and then this one x4. Okay, so you can see that 0 is actually is -1 plus 1 times 4 over 4, which is 0. And then x2 is -1 plus 1 times, 2 times 4 over 4, which is -1 plus 2, which is 1, and then so on. Okay, so meaning you are adding this delta x by 1 by 1 by 1 by 1 in our drawn example here. Okay, and then how about the next one? Okay, so how to compute the next one? So you need to pick some point xi star, okay, in between this region here. Okay, so what should we do here? Okay, what should we do here? So, well, I mean, like, we just do what we did in the previous case. We just pick one of the endpoint is enough. We just pick xi. So we just choose xi star, okay, to be just xi. Okay, meaning the right endpoint. Okay, so this is the right point of the base. Okay, left or right? Either left or either right. Depends on what you want to see later. Okay, so let's compute this. This is equals to 2 times -1 plus 5 of 4 squared minus 8 times squared. And then multiply by the. So I think you can expand it. We should get 10 minus 48i over n plus 32i squared over n squared. Okay, a bit daunting, a bit scary, but for sure later you will see that this compute to something very nice. Okay, then what do you do here? Actually you sum it up. Get some of this scary sum here. So what do you get? So if you expand it a little bit more, so you will get this sum here using the linearity. Okay, and use what we learned for the sigma notation and the formula. You have to get 40. So you need to do a big word. So there we get 40 minus 96 on over n plus 64 times n plus 1, 2n plus 1 over 3n squared. Become a bit more scarier. Okay, but for sure this will compute to some number, like what I assure you just now, right? So what's this integrand here? This integrand is here is defined to be the limit of this finite sum. Okay, so can you imagine that actually a lot of term will go to 0 under this limit here? So let's do this limit, chapter 1. Okay, so thanks to these denominator, right? Most of them here will disappear. So let's quickly see who disappear. So you get 96 minus 96 over n. Okay, how about the other one? You get 64 times a, maybe let's expand it first. 3n squared. Okay, and then I think this is very nice now. 64 times 2 over 3 plus 1 over n plus 1 over 3n squared. Okay, so there's only few terms here can survive, right? These terms are already disappeared. So for the rest, it's just constant. If you add them together, it's negative 40 over 3. Like that. Okay, so this is the first step here. Okay, any question so far? Maybe you can verify the calculation yourself later, but here you follow the step, any step you miss. Okay, if you miss any step, you should ask now. But for the calculation itself, you can verify yourself. Okay, so I can follow the step for now. Is that okay? Is the step okay or not? Okay, so first you get your delta x by dividing your length of your interval by n, and then you choose your xi, and then how to choose xi star, because xi star is just some point in between xi and xi plus 1, just pick xi, it's fine. And then you compute what the finite sum here, the area of the rectangle for first. So this is the area of the rectangle. Rectangle is f of xi star times delta x, and then the next one is the sum of area of rectangle, and then the last one is the limit of sum of area of what kind of rectangle? Refine and refine. Okay, so this is the step we are taking. Or refine, yeah, refine. Or refining. Maybe choose refining because it's keep changing. Okay, so this is the definition, but later on we will learn how to compute this using some technique. Okay, we will learn how to compute this number using technique, which is the thing that correspond to the antiderivative that we have done last week, the last part of the derivative chapter. Okay, any question? before we finish? Again, if you have more questions, we can leave Friday and we can do it together. And see you on Friday.
Sure.